Good day, students. Today we are going to be looking at chemical equilibrium. Please watch this video to the end in order to get a full understanding right to this topic. Now, before I go into the definition, you should understand that we have some reactions what we call reversible reactions, and you have what we call closed system. Now, in a closed system, most reaction tends to have the ability to proceed to both forward and backward directions. Now, a reaction that can proceed to both forward and backward direction is called reversible reaction. Example is this reaction you have here, A plus B to give you C plus D. We use M, N, and PQ at their respective stoichiometric coefficients or numbers of moles of A, B, C, and D. Now, this first stroke here is called the forward reaction. This backward stroke is called the backward reaction. Now, this C plus D is the product. This A plus B is the reactant. Now, this means that if the reactant react to form the product will react back to give you back the reactant. That's what I mean by reversible reaction. So most system tends to be reversible in a closed system. Now, equilibrium or chemical equilibrium now is a state in which both the reactant and product are present in concentration and have no further tendency to change. Equilibrium, chemical equilibrium now is the what? Is a state in which both the reactant and the product are present in concentration has no further tendency to change. Now, this equilibrium or chemical equilibrium is or can be affected by the following: temperature, pressure, and concentration. And it is not usually affected by the term catalyst. Now, that means that catalysts do not affect the equilibrium position of a chemical reaction. But catalysts will affect the rate at which the reactant will form the product, or maybe the rate in which you attain the equilibrium, but will not affect the position of the equilibrium. So, chemical equilibrium is not affected by the term catalyst. Take note of that, it's very, very important. We have homogeneous and heterogeneous equilibrium. Now, what is the meaning of homogeneous equilibrium? Homogeneous means something that is something like the same thing, or let's take it to a reaction. Now, when you have a reaction, chemical reaction, in which both the reactant and the product are present in the same nature, the reactive species are present in the same nature, or they are in the same phase. Remember, the phase of matters can be liquid, solid, and gas. So we have the gaseous state, the liquid state, and the solid state. So if everything is solid, or everything is liquid, or everything is gaseous, such reaction or such equilibrium that will be attained will be termed homogeneous equilibrium, because the reacting species are in the same phase. Take note of that. So if everything is solid, I will give you some examples. Now, heterogeneous means one or more of the reactive species is present in another or a different phase or different state, or the reactive species are not in different state of are not in the same state of matter. Examples can be as follows. Examples are as follows. We have this first reaction, second, third, fourth, fifth, sixth. Okay, fifth. Now we check the nature of the reactive species. Here we have the gaseous, solid, gaseous. So everything are not in the same phase. So this type of equilibrium now is called heterogeneous equilibrium, because the reaction is not, the reactive species are not in the same phase. Let's look at this. We have solid, gaseous, solid, gaseous. The same thing with this, heterogeneous. Now let's look at this. We have gaseous, solid, gaseous, gaseous. We have one solid inside. Everything is not present in the same state of matter. So this is also heterogeneous. We have aqueous, aqueous, aqueous. So this is homogeneous, since everything, all the reactive species here are present in the same phase. Now this we have gaseous, gaseous, gaseous. This is also heterogeneous. because everything are. This is also homogeneous. This is homogeneous because everything is present in the same phase. This is homogeneous because they are present in the same phase. But this and these are heterogeneous because they are not in the same phase. The same thing, we have solid, gaseous, solid, gaseous, everything they are not the same. But we have aqueous, everything is in the same phase, homogeneous. Gaseous, everything is in the same phase is also homogeneous. Now we also have the laws of mass action. Now, equilibrium law, or if you want to check how temperature, pressure, and gravitation do affect the equilibrium position of the chemical reaction, we will call the Chateliers principle. But if you want to write the equilibrium constant of a given reaction at equilibrium, we use the law of mass action. What is this law telling us, or what is this law actually trying to say? The law states that for a given reaction at equilibrium, the arithmetic product of the product, terms in product, divided by that of the reactant, and each raised to the power of their stoichiometric coefficients or numbers of moles in the balance equation is constant. I repeat, law of mass action states that for a given reaction at equilibrium, the arithmetic product of the product divided by that of the reactant, each raised to the numbers of moles or their stoichiometric coefficients in the balanced equation is equal to constant. And that constant is what we call the equilibrium constant, which is Kc. So equilibrium constant for this reaction now is you take the product of the reactant, the product of the product. Now what is the product? Arithmetic product of the product. Now what is the arithmetic product? Multiplication. Multiply C times D divided by A times B. Raise everything to the power of their coefficients. C raised to power P, D raised to power Q, A raised to power M, B raised to power N. So everything you are going to have there will be a constant, which we call the equilibrium constant. Now let's see how to write the equilibrium constant of some specific reaction. And please note, when writing equilibrium constant, the pure concentration of pure liquid or solid should be ignored. For example, if I want to write the equilibrium constant of this, I will ignore the solid. For this, you ignore the solid. For this, you ignore the solids. And anything solid or pure liquid should be ignored. So let's check how to write some special or specific chemical equilibrium constant for some given reactions at equilibrium. Now, if you look at this first reaction, we have this plus this to give us this. Now if you check, this carbon is in solid state, gaseous. So you take the products. We have just one product here, which is CO, carbon dioxide. Then raise it to the power of the coefficient, which is 2. We have CO2 carbon dioxide times this C carbon. But this carbon is solid. So what you need to do now, anything after you have written the equilibrium constant, which is the product divided by the reactant, then raise them to the, because coefficient is 1, coefficient is 2. Then you will now remove the solid. That's why I cancelled out this carbon. You will now be having this. So this is the correct equilibrium constant for this reaction. Now let's look at this. We have gaseous. Take the product, divided by, you multiply the reactant, O2 times this. Then raise each of them to the power of their coefficient. This one is power 2, this one is power 1, because the coefficient is 1, this one is power 2. Everything will be active because everything is in the gaseous state. Now let's look at further. We are going to look at now how temperature, pressure, and the concentration affect the equilibrium position or chemical equilibrium for a given chemical reaction at equilibrium. Now, from the Chateliers principle, which states that for a reaction at equilibrium, if any of the factors such as temperature, pressure, or concentration is altered or is changed, the equilibrium position will shift as to oppose this change or annul this change or counter this change. So it's either going to shift to the right to favor the product, or it will shift to the left to favor the reactant, depending on the case may be. Now first, let's look at the effect of temperature. If you change your temperature, the effect of changing temperature, how does it affect chemical equilibrium? Now, a reaction in terms of heat can either be exothermic or endothermic. Now, when is reaction endothermic? If delta H is negative, it is exothermic. If delta H is positive, it is endothermic. Now, if a reaction is endothermic, listen to this very well. Well, the state we are now, we'll be making one statement. We'll be using one statement to mean two things. So be careful. If I'm mentioning the opposite of +1 is -1. So if I'm mentioning +1, you know that the opposite is -1. If I'm mentioning -20, you know that the opposite is +20. So just words and opposite now. That is what we are going to use to explain this. Now, if a reaction is exothermic, an increase in temperature will favor the backward reaction. That means if you decrease the temperature, it will favor what? The forward reaction. It's just opposite of the one we said before. If we are saying increase favor backward, automatically in the same way, vice versa, decrease will not favor forward. So please take note of that. It's very, very important. So for exothermic reaction, in which the H will be negative, if you increase temperature, you favor the reactant. If you decrease the temperature, you favor the product. That means if you want to have more product for this kind of reaction now, you have to decrease the temperature to have more product because it is exothermic. For exothermic reaction, it decrease the temperature, favor the forward reaction, while increase temperature favor the backward reaction. Now let's look at it for endothermic reaction. Reverse will be the case. For endothermic reaction, which is delta H be positive, increase the temperature will favor the forward reaction, while decrease the temperature will favor the backward reaction. For we to have this nitrogen monoxide now, we are going to have to increase the temperature because the temperature or the delta H here is positive. The reaction is endothermic. So you have to increase the temperature to have more product or decrease the temperature to have more reactant. That is that for our effect of temperature. Please take note of that. For exothermic reaction, increase temperature forward, backward, decrease temperature forward, forward. For endothermic, increase temperature forward, forward, decrease temperature favor the backward side. Now let's look at effect of change in pressure. Now the effect of change in pressure works with the numbers of moles of both the reactant and the product. You calculate how many moles you have for the reactant and how many moles you have for the products. So an increase in pressure will favor the side that have lesser numbers of moles. Take note of that statement. While a decrease in pressure will favor the side that have higher number of moles. An increase in pressure will favor the side that have lesser number of moles, while a decrease in pressure will have to favor the side that have lesser number of moles. So if we have this reaction now, like what we're having here, we're having the nitrogen reacting with oxygen, reacting with hydrogen to form ammonia. So have one molecule of hydrogen reacting with 3 molecules of 1 molecule of nitrogen reacting with 3 molecules of hydrogen to form ammonia, or in gaseous state. Now, one thing you should also note about effect of pressure is that pressure will only affect reactive species that are in gaseous state. So we only take the concentration of gases here. Any other thing like solid or liquid, we will ignore them when we are looking at effect of pressure. Take regards only to the reactive terms in gaseous states. So everything they are in gaseous state, they will count. So you calculate how many moles of the reactant do we have. 1 mole of nitrogen plus 3 mole of hydrogen will give us total of 4 moles. How many moles of ammonia? We have 2 moles. So for you to have to favor, if you want to favor the forward reaction now or the product, or if you want to have more products, what you need to do is to increase the pressure or decrease the number of moles or remove more ammonia. If you remove more of this ammonia that is being formed, then the equilibrium position will shift to the forward side. If you also increase the pressure, it will also shift to the forward part. If you increase the amount of this ammonia, if you increase the amount of this ammonia, maybe you add more ammonia to the system, the equilibrium position will shift to the what is it called, the reactant. Or look at this second reaction. We're having 1 mole of the reactant, we're having 2 moles of the product. So if you want to favor this forward side, now what do you need to do? Remember, if you want to first of all check what are the natures of the reacting species. The nature of this one is gaseous. We're already good to go. Then next, how many moles of reactant do we have? We have 1 mole. How many moles of product? We have 2 moles. So if you want to have more product now, you have to remove more of the products, or what do you need to do? You decrease the what is it called? The pressure. If you increase pressure, the pressure will go and favor the side that have lesser number of moles. But if you increase the pressure, the equilibrium position will shift to the left. If you decrease the pressure, it will shift to the right hand side, because it decrease the pressure will favor the side that have higher number of moles, while increase pressure will favor the side that have lesser number of moles. For this one is solid, it will not count. This one is solid, it will not count. So we have 4 moles of, this one is gaseous. So we have 4 moles of the reactant, we have 4 moles of the product. Since the moles of the reactant and the product are the same thing, equilibrium for pressure will have no effect on this. Let's also check this one, the same thing. 1 mole plus 1 mole, we have 2 moles. 2 moles here, we have 2 moles here as well. Pressure have no effect for this. Then let's look at this. We have 3 moles of the reactant, we have 2 moles of the product. For you to favor the forward side now, you have to increase. If you increase pressure, the equilibrium position will shift to the side that have lesser number of moles, which is these 2, which is product. If you also remove more of this product, then you also shift to the what's it called, the left and the right hand side. But if you want to have more reactant later, if you want the equilibrium position to shift to the left hand side, you increase the pressure, because increased pressure will move to the side that have the higher number of moles. Look at effect of change in concentration. Now, for effect of concentration, what you need to know is that if you increase the concentration of the reactant now, more product will be formed. So equilibrium position will shift to the right. If you increase the concentration of this one now, it will shift to the right. If you decrease the concentration of this, it will shift to the left. It's still the same, almost the same thing. Equilibrium position will shift to the side that have lesser concentration. So if you decrease the concentration of this one, now this one have lesser, you shift to that side. If you increase the concentration of this one have, for this one not to have less, you move to the forward side. So if you increase the concentration of the product, the equilibrium position will shift to the reactant. If you increase the concentration of the reactant, equilibrium position will shift to the product. So for this now, if you increase the concentration of, that means if you add more of this CaCO3, more of this product will be formed. Let's look at more examples on this. Now, we have 2 processes now which we'll be looking at in equilibrium in practice. Now we have the Haber process, we have the contact process. We also have survey process. When you use limestone to make a carbon dioxide, you have survey process. Then let's look at Haber process is when you use 3 moles of hydrogen gas combined with 1 mole of nitrogen gas to form 2 moles of ammonia. Contact process is when you use 2 moles of sulfur dioxide, mix it with oxygen to form 2 moles of sulfur trioxide. So this is called contact process, this is called Haber process. Now for this now, for you to have more products, what you need to do, number 1, you have to either increase the pressure or increase the concentration of the reactant. So if you add more hydrogen to this reaction now, more of the equilibrium position will shift to the right in order to form more ammonia. But if you decrease the concentration of the reactant, the equilibrium position will shift to the left. So that's how it is. The same thing with this. If you increase the concentration of this one now, of this reactant, more product will be formed. If you also increase pressure for this, more product will be formed. For this one, increase pressure, more product will be formed. So what you need to do, you have to understand these things. It's very, very important. So if there's anything you don't understand, you can put it in our comment section or watch this video over and over again for more understanding. Thank you. God bless you.